Hello, everyone. Thank you for joining us today. We're excited to present to you our AAAI tutorial on explaining machine learning predictions. I am Julius Adebayo.
I'm Lakkaraju.
And I'm Singh. Check out the companion website we have with all the links to slides and references. I hope you find this tutorial useful. So let's begin.
In the past decade or so, machine learning models are being increasingly used in a variety of real-world applications. For example, these models are being used to assist decision makers like doctors and judges in domains such as healthcare and criminal justice. These models are also being used in other domains such as financial lending to determine which applicants get their loans approved. In addition, machine learning models are powering several popular online platforms, including Amazon, Facebook, Goodreads, and many, many more. So basically, machine learning is everywhere today. Now, out of all these different applications and settings, model understanding is absolutely critical in those domains which involve high stakes decisions, which can impact the lives of millions of individuals. Examples of such domains include healthcare, criminal justice, financial lending, and so on. Let's try to dig deeper and understand why we really need model understanding. Let's take an example to begin with. So in this case, let's say we have an input image which is being provided to a predictive model, which in turn predicts what this image is. In this case, the predictive model is rightly predicting the label as Siberian Husky. All seems good so far. But if we only probe deeper to understand how the model is making this prediction, we might actually find things that are surprising. For example, in this case, we might see that the model is using the snow in the image to make its prediction. So clearly, this is a spurious feature that the model is relying on. If a particular model designer has this kind of an understanding or input, he or she might quickly realize that the model is basically using incorrect features in making its predictions and might go back and debug the model and also make it better, right? So in this example scenario, model understanding is facilitating debugging. Now let's consider another example where we have a defendant. Let's say we have a lot of details about this defendant, including her prior criminal history and socioeconomic information and so on. Let's say that there is a predictive model which basically takes all this information as input and outputs if a particular defendant is risky to release on bail or not. Okay. A judge is at the receiving end of this prediction, and if we just provide the judge with this singular prediction, the judge might not exactly know how to interpret this prediction and if and when to trust this prediction. On the other hand, if we provide a deeper knowledge about how this prediction is being made, then that might be helpful to the judge. For example, in this case, if we provide judge with a set of the most important features, which unfortunately happen to be race and gender, the judge would quickly realize that this model is biased, or at least this prediction is biased, and that race and gender are being used predominantly to make this prediction. And therefore, the judge would just discard the model's prediction and make his or her own decision in this particular case. So in this example, model understanding is facilitating bias detection. Now let's consider another example scenario where we have a loan applicant, and we again have all the details about this applicant, like their financial status, socioeconomic status, and so on. Let's say that there's a predictive model which takes all this information and determines if an applicant should be given a loan or not. So let's say for a particular applicant, the model denies loan. Instead of just telling the applicant that his loan is denied, it would be helpful to give more information which can help the defendant get some recourse, right? So in this case, maybe telling the applicant that increase your salary by 50K and pay your credit card bills on time for next 3 months, and then you can reverse this decision, or you will be able to get a loan. That information can be super useful to the applicant. So in this particular context, model understanding is helping with providing recourse to individuals who are adversely affected by model prediction. predictions. Now let's consider another scenario where we have a bunch of data about different patients, and then there's a predictive model which is outputting if a particular patient is healthy or sick. So that is the kind of prediction the model is making. Now, again, if there is a doctor who is at the receiving end of these predictions, the doctor might not really know if and how much and when to trust these model predictions. Now, let's say the doctor has a deeper understanding of what the model is doing. So, in this case, the model is actually using ID numbers to predict if a female patient is sick or not. But in the case of male patients, the model is using the right kind of features like cold and cough to determine if they are sick or not, right? So if a doctor sees this deeper understanding or gets this deeper understanding, the doctor can quickly determine that this model is using irrelevant features when making predictions on female subpopulation, and therefore she should not trust the model's predictions on this particular subgroup. So in this case, model understanding is helping the doctor assess if and when to trust model predictions when making decisions. Now let's look at the other side of the picture where there is a regulatory agency which is trying to determine if this model should be approved for broader deployment, for a more large scale deployment, right? And if this regulatory authority has this information that the model is actually using spurious features like ID numbers to make predictions on female subpopulation, the regulatory authority or agency might just determine that this model is probably not ready for a more wider or large scale deployment and might reject their approval or deny the approval, right? So in this case, model understanding is allowing us or the regulatory agencies or authorities to vet models to determine if they're suitable for deployment in the real world. Okay. All right, so clearly model understanding has a lot of utility. It is helping with a variety of things, including debugging, bias detection, providing recourses, helping people understand if and when to trust model predictions, and also helping us with vetting models to assess their suitability for deployment. In enabling all these use cases, model understanding is helping a variety of stakeholders, including end users such as loan applicants, decision makers such as doctors and judges, regulatory agencies like FDA, and even machine learning researchers and engineers so that they can debug their models and improve their models, right? So now the next big question that we want to ask ourselves is, given that model understanding has so much utility, how do we actually achieve model understanding? Right? In order to do that, at a very high level or a broad level, two kinds of approaches have been proposed. The first approach is build models that are just inherently interpretable. For example, models like linear models with very few non-zero coefficients, shallow decision trees, simpler rule-based models with a handful of rules. These are all often known to be inherently interpretable because an end user can look at these models and get a rough idea at least of what the model is doing or how it is making predictions. Now, the other kinds of approaches involve explaining pre-built models in a post hoc manner. For example, let's say we have a black box or we have a complex model like a deep neural network with several tens or hundreds of layers. Such models are actually provided as input to explanation algorithms or explainers, which in turn output explanations in the form of simpler models, again, like linear models or shallow decision trees or rule-based models with handful of rules and so on, which are again very human understandable, right? So this is approach 2. Now, the next question that would logically come up is which approach to use when? Should we go for always building inherently interpretable model, or should we go for explaining models in a post hoc manner? In order to understand when to do which approach or when to take which approach, let's again consider an example, right? So in certain settings, we might observe that there are trade-offs between interpretability and accuracy, right? So what we observe is, for example, models like linear regression or decision trees, which are often referred to as simpler models, they might be having a poor accuracy compared to complex models like deep neural networks or random forests, which might be providing a higher accuracy, right? So in this case, if you're going for interpretable models, you're sacrificing accuracy. If you're going for complex models, you're accurate, but you're sacrificing interpretability. Okay, so in certain settings, these kinds of trade-offs may exist. And when these trade-offs may exist, you might want to go for post hoc explanations. Right now, let's probe a little bit more about understanding when exactly do these trade-offs exist, or what kinds of settings call for these trade-offs. Again, to illustrate this, let's consider this example. What we have here is a scatter plot of a two-dimensional data set. On the x-axis, we have dimension 1, y-axis, we have dimension 2, and we just have a scatter plot of all the data points in the data set. And let's say blue colored data points indicate those belonging to class label 0, and lead colored data points belong to class label 1. Now, as you can see from this picture, the data here is such that it is almost linearly separable. So we can probably just fit a simple linear model and then get a reasonably accurate classifier in this case, right? So in such case, we can build models that are both interpretable as well as accurate. So that's amazing. On the other hand, more commonly in the real world, what we observe is the decision boundaries in the data look like this, what you see on the right-hand side, right? So the decision boundaries are highly nonlinear. So the separation between this blue versus red, which are the two kinds of class labels, that boundary is highly nonlinear. In this case, unfortunately, it would not be possible to fit a simple linear model and get a very high accuracy. So these are the settings where we might see interpretability accuracy trade-offs, and complex models might achieve higher accuracy. So in that case, we might want to go with post hoc explanations. There are also other cases which might call or favor post hoc explanations. So for example, sometimes you just don't have enough data to build your models from scratch, right? All you have in that case is a proprietary black box, and that's what we are stuck with. In such settings also, we might have to resort to post hoc explanations. So, in summary, what we would like to say is that if you can build an inherently interpretable model, which is also accurate for your setting, please do it. Right? So that's probably the best way to go if you are able to build a model which is both interpretable and accurate. Otherwise, post hoc explanations will come to your rescue. And this tutorial will focus on post hoc explanations.
So how do we define what an explanation is? Here's a simple definition of what an explanation is. An explanation is any interpretable description of the model behavior. So what does that mean? Imagine a classifier with some complex surface that's shown here in blue and pink. And that's what you have on one side. What you have on the other side is some user that wants to understand this classifier, right? And so this boundary in between is what explanation is. So from the classifier point of view, the explanation should be faithful. So it should represent exactly what the classifier is actually doing. And from a user point of view, it has to be understandable. So the user should be able to interpret and sort of make some inferences about what the classifier is doing. So what could these explanations actually look like? Let's look at a few examples. The most obvious one is to maybe look at all of the model parameters. That is an explanation. It's maybe not a very understandable one, but it is definitely a very faithful one. Here's another one. What about we send many example predictions? That is definitely also an explanation. What if we summarize what the classifier is doing with a program or with a rule or with a tree? That's an explanation. We're going to see some examples of that. What if we select the most important features or the most important training data points? Those are explanations, and we'll see more of those later as well. What if we describe how to flip the model prediction? And those are also a kind of explanation that people use, right? And there are probably many others, some that have been used for a while and some that haven't been studied yet. And so if you're curious about what makes a good explanation, what makes a bad explanation, I would point you to Zachary Lipton's work in 2016. that does a really good job about talking about these ideas. Okay, there's also this idea of global versus local explanations. So far I'm talking mostly global explanation, but in general, they might be too complicated. So if you have a crazy classifier surface like this, you may not be able to explain exactly what's happening, right? So you may not be able to be faithful to this. In that case, what you could do is you can say, well, I don't care about the overall behavior. I care about behavior in context of a specific prediction. So I can take a data instance X and see where in the surface does it fall, and essentially zoom into that local view around that point. And you can see suddenly the classifier surface, at least in this cartoon example, is not looking so scary anymore. And so that's essentially what a local explanation is. It's an interpretable description of the model behavior in a target neighborhood, right? So it's just an additional caveat on top of global explanation is what makes it a local explanation. So what are examples of local explanations? Turns out everything we talked about earlier as global explanation can be a local explanation as long as what it's being faithful to is some target neighborhood, not necessarily the whole model, right? And you can imagine there's a spectrum between being very local and a little bit local and then being completely global. Okay. So that's the essential difference between local and global explanations. Here is some sort of high level reasons why they're different. Just to remind you again, local explanations explain individual instances or individual predictions, whereas global explanations are used to explain the complete behavior of the model. And so local explanations tend to unearth biases in the local neighborhood. So, what's going on for a specific instance or similar instances, whereas the global ones can shed light onto bigger picture biases that your models may have on larger subgroups than just a few instances. And finally, local explanations can be used to vet if individual predictions are being made for the right reasons, whereas the global explanations can help you vet the whole model at a very high level. Is it suitable for deployment or not, right? Is it doing everything for the right reasons? So given that sort of distinction, here's what the tutorial is mostly going to be focused on. Next, we're going to be talking about approaches for post-hoc explainability, slowly go over some of the commonly used methods, talk a lot more about evaluation of how these explanations takes place and what are some of the problems with it. What are, in general, the limits of post-hoc explainability, which is what we've been talking about, and then end with some thoughts on the future directions of post-hoc explainability. Let's start with the first section, approaches for post-hoc explainability. In this section, we'll cover some of the commonly used techniques and give lots of examples of what these explanations look like. So this is sort of the structure of this section. We're going to talk about local explanations first, a bunch of different ways of doing those, followed by global explanation techniques and different ways people have approached that problem as well. And yeah, give lots of examples for each of those. We'll start first with feature importances that we'll distinguish from saliency maps, although they're similar, and give some examples of methods that give you feature importances. Before I go into too much detail there, I want to make sure the methods we'll be talking about in this section will be all model agnostic methods, or in other way to say that is they're going to be black box methods. The idea here is that you're not going to have any access to the internal structure of the model. So given a data point, you can send it to the model and the model sends you back a decision, and that's all you know about that model. So why would we want to do this? Why would we want to constrain ourselves so much when we're creating these explanations? Turn out there are some really nice advantages to doing that. Firstly, it makes it so that your interpretability technique or the explanation technique is not restricted to specific models, which is nice because the models keep changing over time. The models, architecture keeps changing over time and so on. They're also practically very easy because you're not tied to any underlying library or implementation. You can just use it on any model that you are trying to explain. And finally, you can also study models that you don't even have access to. And this sometimes is essential, depending on what the pipeline is. Okay, so the first method I'm going to talk about is called LIME that we introduced 5 years ago, I guess, at this point. And the idea here is to look at this local region, and this is an example, and try to approximate it with a sparse linear equation or a sparse line. And so this is what it looks like. And the idea for picking a sparse line is to essentially identify the important dimensions, which means the sparse part, and also present their relative importance, which is what the linear part would be. Okay, so how do we actually do this? Let me walk you quickly through the example explanation and show you how the algorithm works. So here's an image of a dog playing a guitar, and the model says that this is a Labrador image with some probability, right, 0.21. Now we want to explain, why does the model think so? Why does the model think this is Labrador? What Lime does is takes this image and creates a bunch of perturbations. So here's a single perturbation, and it looks at what effect does it have on the model output. Well, it turns out the model probability went up in this case. Makes another perturbation, looks at the model probability, makes another perturbation, looks at the model probability, and essentially creates a mini data set of these perturbations and the output of the model. Once you have that, you can essentially train a sparse linear regression on this mini data set that you have collected, right? So what has changed? You're trying to learn coefficients for each of those. And essentially you get an explanation where the grayed out area are the superpixels that were zeroed out. And the ones that are shown are the one that had a high enough coefficient. So that's the reason the model thinks it should be a Labrador. What is nice about Lime is that it's extremely customizable. And some might say that this is also the problem with Lime. What is customizable? Well, in this case, first thing you have to pick is, how do we perturb these images, right? Or whatever you're trying to do, you have to perturb it, and there's a lot of flexibility there. What is the distance, or what is the similarity function in order to do the locally weighted regression? This is something that the user can come in and change. How local do you want the explanation to be? Is it supposed to be very, very local or slightly broad? That's also something that the user can specify. And finally, how do you actually even want to express the explanation? Do you want to use pixels, or do you want to use superpixels, or do you want to use something else? That's also something that the user can specify when they're using Lime. And so the question is this too customizable or not? And we'll talk about that a little later. Here are some examples of one example of what an explanation looks like for Lime. Here's a simple task where you're trying to differentiate between wolves and huskies that look very similar. And turns out this model seems to be reasonably good. It's only making one mistake, but you have no idea why it's working and why it's not working in that specific instance. Here's what an explanation looks like, and you don't have to look at all of this right now, but essentially look at the ones where the model predicted it to be wolf. And you will realize that in the explanation, the wolf part is actually hidden. It's all grayed out. And the model is looking at everything else in that image. And in all four of these, you will see that's basically snow. And so you can sort of conclude by looking at these Lime explanations that what you've done is built a great snow detector that predicts wolf every time there is snow, completely ignoring the animal, whereas predicting husky otherwise. Along with Lime, there was also a different explanation technique that came out called SHAP, which is essentially Shapley values as importances. It's very similar to Lime in that it requires you to make perturbations to the input and looks at the black box behavior of the model to figure out which features are important and which features are not. The difference is that instead of learning regression and anything like that, it's basically computing a marginal contribution of each feature towards the prediction, sort of averaged over all possible permutations. That's sort of the theoretical definition of what SHAP is trying to do. So here are here's one sort of example of how this works. Suppose you're looking at a specific perturbation O here, and then some features are on, some features are not on. You can look at what the model output is, which is 0.9. You also look at the perturbation with this feature xi removed, and you look at what the output of the model is. Turns out it has gone down, it's 0.8. So the marginal contribution of xi for this permutation ends up being 0.1, which is the difference of the two, right? This is just the marginal contribution for one permutation. If you average it out over all permutations, you get the overall marginal contribution of xi. and that will tell you how important xi is. What is nice about this is there is a lot of theory here to show that this is the most fair way of attributing importance to features or to predictions, attributing predictions to features. Yeah. Okay. So those were some examples of feature importance-based methods. I quickly want to give you some sort of view of what rule-based explanations look like. What we'll essentially be talking about are anchors, which is some work we did 3 years ago at AAAI, actually. And the idea here is to look at surfaces, again, local surfaces, and maybe the local surfaces don't look linear, but you still want an explanation that you can understand. So what anchors does is tries to find the sufficient conditions for the prediction to stay the same. What this means is, in this case, what are the conditions under which, as long as those conditions are true, with high probability, you'll have the same output. So it's a little bit abstract. Let me give you a quick example of what this looks like. Here's a task where you're trying to predict the salary of a person based on a bunch of demographic details. And for this instance, the salary looks like it should be less than 50K according to the model. Now, if we look at why this is the case and ask Lime for it, Lime sort of gives you what were the most important features, says that capital gain being 0 was why it thinks it should be less than 50K, marital status is more than 50K, and so on. And this is nice to look at, but it doesn't really tell you exactly what's going on. Specifically, it doesn't tell you what you need to do to change it, or what do you need to sort of what is happening in this for instances like these, right? What anchors does, on the other hand, is gives you a very simple rule, such as if education is less than equal to high school, then predict less than 50K. And that clearly communicates exactly what the model is focusing on, where as long as education is not enough, the model seems to be predicting the salary should be small. So those were some of the simple rule-based methods. And now I'll let Julius take over.
We'll now move to a discussion of saliency map approaches. So let's say we're given a model noted as F data here. Think of this as an inception V3 model trained on ImageNet, and it gives a prediction of Junco bird on this particular input. One question we might be interested in is, what are the parts of this input that are most relevant to the Junco bird prediction? And this question is exactly what saliency map, feature attribution, or heat map methods address. For the rest of this section, we'll call them saliency map techniques, but they're also known in the literature as feature attributions. So let's look at a variety of different methods that do this. One of them is the input gradient, and this is actually a key primitive to several other methods. And the input gradient corresponds to the derivative of a particular logit score for a given class with respect to the input. And this gradient is the same size as the input, and you can visualize it in the form of a heat map, which is often called a saliency map. Now, with the input gradient, there are a few challenges. One of them is that it seems visually noisy. The second one is that the gradients violates a sensitivity requirement, also known as gradient saturation in the literature. This is the fact that changes from one input to another that induce changes in the output might not be reflected in the actual gradient. And so several other methods have been proposed to counteract this. For several of the methods we'll now talk about, we'll sort of give a quick overview of them due to the time limit here, and we'll refer to additional sources where you can learn more about those methods. So the first method is smooth grad, and smooth grad corresponds to an average of the input gradients of noisy examples. And so moving forward, we have integrated gradients. Integrated gradients compute a path integral from a baseline all the way to the input you want to actually explain. And so this integral in practice corresponds to summing up the input gradients from the baseline all the way to the input of interest. So a different class of methods are known as modified backwards approaches. If you step back to think about how to actually compute the input gradient, you realize that this just corresponds to issuing sort of a gradient call to the backpropagation algorithm in your favorite autodiff package. And so what this modified backprop approaches do is they modify the backpropagation process with different rules for computing feature relevance. And so one of them is guided backprop. For a ReLU network, guided backprop turns on the forward ReLU and the backward ReLU while performing the input gradient computation. And when you actually visualize the saliency map in practice, you see that it's sparse compared to original input gradient. And this is the result of turning on the forward or the backward ReLUs. So we also had a larger class of modified backpropagation approach. This is known as the layer-wise relevance propagation, in short LRP. These methods decompose the output iteratively layer by layer all the way to the input. And they do so with a variety of different rules, the epsilon rule, gamma rule, and other kinds of rules. And so if you visualize a bunch of these different rules, you see that they correspond to the saliency maps that we show here. So to give you a quick recap of what we've just gone over, we've looked at LIME and SHAP. We've also looked at a variety of different saliency approaches. So while we've looked at these different approaches, these are not the only saliency methods in practice. These are just a fraction of the vast amount of methods that currently exist for computing feature attributions and saliency maps. And so we'll refer you to the overview work of Samek and Montavon from 2020 that gives a nice overview of several of these additional methods. So let's move to a discussion of prototype methods now. So prototype methods are post-hoc explanation methods that explain a black box model or a function with either synthetic or natural input examples. And so these methods can be used to answer questions like which of the training samples are mislabeled, or generate synthetic or natural examples that maximize a particular intermediate neuron. So the first method we'll talk about here is training point ranking via influence functions. And so you can think of this method as answering the question, given an input, can you rank the training points that have the most influence on the test loss for a particular new input? And so let's say we have this Junco bird that has been predicted correctly as a Junco bird by this model, F data here. We can ask, now we want to know the training examples that have the most influence on the test loss of this input. And when you do that, let's say we hypothetically do that for the model and we see these top 3 ranked examples. And if you're a developer that is inspecting this model, you can have more confidence that the model is actually relying on the Junco birds in the training set to also predict a Junco bird here, which sort of indicates that the model is relying on the right semantic features. So to summarize the sort of the underlying techniques behind the influence functions, it sort of derives from an influence function, which is a classic tool in robust statistics for assessing the effect of a sample on the regression parameters. What Ko and Liang did in their ICML 2017 paper was to take the inspiration from this tool and bring it into the modern machine learning set by deriving analytical formulas for the influence of a training point on the parameters of a model and the training point on the test inputs loss. And so there are a few challenges. One, it can be difficult to scale this influence function computation to models that have millions of parameters. And then there could be an issue with deeper models due to non-convexity. And more recently, there have been several other approaches that also try to answer the training point ranking question. So representer points by Ye et al. And the recent work tracking by Pruti et al. That appeared at NeurIPS 2020 also are alternatives. So let's shift to activation maximization. So activation maximization methods are explanation methods that use either synthetic or natural examples to sort of indicate what kind of example strongly maximizes a particular function or neuron of interest. And these kind of explanations come in 2 flavors. One, the kind of explanation method that search through a corpus of examples to see which one maximizes a neuron, and then another class of methods that sort of do optimization via gradient descent to synthesize a synthetic input that actually maximizes a function of interest. And so here we're showing an example of these two approaches. In the first row, examples of natural images that maximize a neuron in inception, and the second row, an optimization process due to Ola et al. In 2017 that synthesized examples that actually maximize a particular neuron. And so with this discussion, we end our overview of prototype examples. Thank you.
All right, now let's talk about local counterfactual explanations. As machine learning models are being increasingly deployed in various real-world scenarios, particularly those which involve high-stakes decisions, it is becoming extremely crucial to provide recourse to affected individuals. And this is exactly what counterfactual explanations are designed to do. More specifically, counterfactual explanations capture what features need to be changed and by how much to flip a model's prediction. That is, to reverse an unfavorable outcome of a given predictive model. To understand this, let's consider a concrete example where we have an applicant who is applying for a loan to a bank, and the bank in turn is using a predictive model denoted by f of x to decide which loan applications will be approved. In this case, let's say this particular applicant's loan application is rejected by the predictive model. Now, what we are talking about here is to design counterfactual generation algorithms which interact with the predictive models to provide recourse to such affected individuals. In this case, this applicant could potentially get a recourse that takes this form, where the algorithm is asking him to increase his salary by 50K and pay his credit card bills on time for the next 3 months. Now, how to even design such algorithms? So what is the intuition behind that? In order to understand that, let's look at this picture. What you see here is the decision boundary of a particular predictive model, and X is the instance for which we are trying to find the counterfactual. The underlying logic behind a lot of the counterfactual generation algorithms is pretty simple. It is to basically take this instance X and keep making very tiny modifications to it until it crosses the decision boundary over to the positive side, right? So that's pretty much what a lot of these algorithms do. And the main aspect where these algorithms differ on is how to choose among various candidate counterfactuals. For example, what you see in this picture is that CF1 and CF2 are both valid counterfactuals for X, which one to pick, right? So that choice is where most of the algorithms differ. So Wachter et al. Proposed the first solution to finding such counterfactuals, and what their objective tries to do is again something very intuitive. So for an instance X, they try to find a counterfactual X prime such that f of X prime is the desired outcome. That is, the predictive model outputs the desired outcome on X prime, and X prime is chosen in such a way that the distance between X and X prime is as small as possible. Now, it's easy to see that the choice of the distance metric dictates what kinds of counterfactuals are chosen, and Wachter et al. Advocate for normalized Manhattan distance. Here are some examples of the counterfactuals generated by Wachter et al. And what we see in a couple of these cases is it is asking individuals to change their race to obtain recourse, which, as we all know, is not feasible. Right? In order to fix this problem, Uston et al. Proposed a new objective. Here, end users can actually input constraints in order to generate feasible counterfactuals. For example, end users can actually say that changes to race and gender are not feasible, and that constraint will be respected when finding counterfactuals. Furthermore, instead of basically using an L1 or L2 distance function, what Uston et al. Advocate for is to use this notion of cost, which captures how hard it is to go from X to X prime. And they advocate to pick counterfactuals using such a cost function. And here is an example of a counterfactual or a recourse produced by their algorithm. Let us focus on this current debt part here, where they're asking an individual to reduce the current debt from $3,250 to $1,000. Let's see if this has any other negative implications. Okay? So here is this individual who is being asked to reduce his debt, as we just talked about. Now, let's say this individual comes back after an year and says, okay, now my current debt debt is finally reduced to $1,000, please give me a loan. Right? What might happen is that the model and the counterfactual generation algorithm might say, well, your debt decreased, but your age increased by 1, so we can no longer, give you the loan because your counterfactual is not valid. Now, what has happened here is that the feature interactions have not been accounted for in Uston et al.'s algorithm when generating counterfactuals, right? So this is very critical to account for in order to generate feasible counterfactuals, but how do we do it? And one of the solutions proposed is to basically leverage the underlying causal models. So these underlying causal models capture interactions between the features, and if we leverage those when defining our distance metrics, we can potentially mitigate these kinds of problems. All right, let's now talk about global explanations. Global explanations are designed to explain the complete behavior of a given potentially black box model. The goal of such explanations is to provide a bird's eye view or a big picture view of model behavior. And why is that helpful? This can be extremely helpful in detecting big picture model biases which are persistent across larger subgroups of the population. And this is typically incredibly hard to do with local explanations because that would involve manually inspecting local explanations of several instances, which is pretty impractical. So, in that sense, global explanations are often considered to be complementary to local explanations. Now, let's look at some of the approaches that have been proposed to actually construct global explanations. The first idea is to think of global explanations as some collection of local explanations. And how do we do that? The first step in doing this would be to generate a local explanation for every instance in the data using one of the approaches that we discussed earlier. And then once we have all these local explanations, we then pick a subset of K local explanations which constitute the global explanation. Okay, let's consider a particular method called SP-LIME, which actually tries to do something similar. And SP-LIME uses LIME underneath as the local explanation technique. Okay, by now we all know that LIME explains a single prediction. That is, it explains the local behavior of a given black box model around the vicinity of a single instance. Let's say the black dot here corresponds to an explanation. Now, in order to understand the global behavior of a complex black box, it is impossible to examine all the explanations output by LIME corresponding to all the instances in the data. So the idea that we are going to employ here is to instead pick K explanations to show to the user. And how to pick them? They should be picked in such a way that they are representative, that is, they summarize the global behavior of the model well, and also they are diverse, that is, they should not be redundant. For example, let's look at the red, blue, and black dots on the screen right now. Each of those could correspond to an explanation, a local explanation, right? Now, if we pick the black dot or the explanation corresponding to the black dot, it would be redundant to pick the explanation corresponding to the red dot because essentially they correspond to a very similar hyperplane. On the other hand, once we pick the explanation corresponding to the black dot, it would be useful to pick the explanation corresponding to the blue dot because it adds diversity. It captures a new hyperplane, right, which approximates model behavior in a particular local region. So these are the intuitions that SP-LIME captures in a submodular optimization problem and uses greedy algorithm to pick a subset of K local explanation, which constitutes the global explanation. All right, the next approach that people commonly use when constructing global explanations is called model distillation. The basic idea behind model distillation is very simple, and this is as follows. Let's say we have a predictive model f of x. Let's assume that this is even a black box. We don't know any internals of f of x. Now, let's assume we have some input data where we have a bunch of features and values corresponding to several data points. And we can pass this kind of input data through the predictive model and get the model predictions. Now, model distillation typically involves taking all these pieces as input and passing them through an explanation algorithm or explainer, which in turn outputs a simpler interpretable model, which is optimized to mimic the predictions of this black box. Okay, in some sense, the idea of model distillation is to construct a simpler model which can approximate the behavior of this complex model. And people have come up with different techniques to do this. For example, there has been work that uses decision trees to approximate the behavior of black box models. There has also been some work on using decision sets to approximate the behavior of complex models using model distillation. And similarly, there has been literature which proposes using generalized additive models to approximate the behavior of any given black box. And a generalized additive model basically helps us capture the relationship between the input variables and the output variables. That is, for each input variable, we see how the output variable varies as a function of the input variable. Okay. All right. The other approach is about the summaries of counterfactuals. Remember that we talked a lot about how local counterfactual explanations are extremely important for providing recourses to individuals, right? Now, why are global summaries of counterfactuals important? They are important because sometimes we might have big picture questions about counterfactual. Say that we have a regulatory authority who wants to ask big picture questions, for example, to understand if there are any biases in the recourses being provided against certain demographics, right? In some sense, this regulatory authority might want to ask how recourses permitted by the model vary across different racial and gender subgroups. In order to provide answer to this question, we need algorithms for generating global summaries of counterfactuals, and such a summary could look like this. So what you see here is the outer if-then rules correspond to descriptions of the subgroups of the population, and the inner rules correspond to the recourses being provided to individuals from the corresponding subgroups. A quick look at this basically demonstrates that if you're not a Caucasian, the recourses are asking you to change much more features or many more features than if you are a Caucasian, right? So clearly there is a bias in the recourses. And if a regulatory authority sees this, they'll quickly realize that there is this kind of a bias against certain demographics. So maybe this model itself is not a good idea. And Raval et al. Proposed an algorithm to do this. They basically formulate an optimization problem, which is non-monotone and submodular with matroid constraints, and solve it using a well-known algorithm called smooth local search algorithm, which has the best known optimality guarantees.
We'll now discuss representation-based explanation approaches. So this class of approaches use the intermediate representations of a deep network to study the model's reliance on user-provided concepts. And so you can answer questions like, does the model rely on the concept green background in this case in order to predict that this input is a junco bird? And so two methods that we'll highlight in this under this class of approaches is network dissection and TCAP. And broadly speaking, the steps of this method include, first, you gather human labeled concepts that represent concepts that you want to detect the model's reliance on. You then collect hidden representations that encode for this concept from the network that you want to study. And in the third instance, you then quantify the alignment between the representations and the human labeled concepts that you've collected. So network dissection has been used to study a variety of different networks like Resonant 152 and to quantify the units in these different networks that encode for house, dog, train, plants, airplanes. And TCAP has also been used to study the GoogleNet and Inception V3 models. And there's been extensions of TCAP to regression, as well as automatic ways to sort of encode, extract concepts from input data. And so with this, we conclude a quick overview of representation-based approaches. And this brings us to the end of the section on approaches for post-hoc explainability.
So now that we've heard about a bunch of explanation techniques, both local and global, how do we know which ones work? How do we know which ones don't work? And for that reason, our next section is going to be on how these models, how these explanation methods are evaluated. Essentially, there is a nice taxonomy that was in that paper in 2017 that sort of talks about how different evaluations take place. And at the very bottom, they start with functionally grounded evaluation, which are the most simplest ones in some sense, where there are no real humans involved and they're all through proxy tasks. And these are the most common way people evaluate explanations. They have a slightly higher level evaluation as well, where some of them are human grounded, where you do these tasks with real humans, where you try to keep the task simple, such as crowdsourcing and things like that. And then finally, they have application grounded evaluation, where you're actually going to people who are deploying models on real tasks and try to get them to see what explanation is useful and what is not. We are going to follow a slightly different structure. Instead of looking at how complicated or how involved the evaluation is, we are going to be looking at what the evaluation is trying to test, or which aspect of explanation is it trying to test. And so these are going to be the three criteria. The first one is going to be, can we understand the behavior of the model using the explanation itself, right? And there are different ways of turning this into an evaluation, and I'll give you an example of some of them. So the first one is to ask the question of how important, if you're selecting a few features, how important are they actually to the model? The idea here is to start with your instance and do some deletion by removing the most important feature according to the explanation and see what happens, right? So here's an example, for instance, of an image, and you have an associated explanation, which is a saliency map in this case. And you want to know what happens when you remove the most important pieces, right? So you draw a graph where you're sort of plotting the prediction probability on the y-axis and the percentage of pixels deleted on the x-axis, and you start deleting pixels, right? So maybe the initial probability is at some point, you find the most important region according to the explanation, remove it, see what happens to the prediction, right? You find the next more important feature, remove it, see what happens. You find the next more important feature, remove it, and see what happens, right? And you keep doing this till essentially you've removed everything in the figure, right? So you've blanked out the figure and you get your sort of final point, right? Now, the idea is that if this curve falls down very quickly, that means your explanation is good because you've picked the most important features, since by removing them, the model probability is falling down. But if it stays kind of flat and then falls, then your explanation is not very good, right? So you can look at metrics like the area under this and so on to figure out if your explanation method is good or not. There's a version of this that also, instead of deletion, does insertion. So you start with a removed image, and then you start putting in your features according to whatever is most important by your explanation technique, and see how the probability of the model goes up, right? And so as you're deleting, it's going up, and eventually it'll reach, you would have inserted all the features, and you have your whole instance, and your probability will be very high. And again, you can look at, if it's a good explanation, then it should really go up fast because you're adding the most important features. But if it's not if it's a really bad explanation, then it'll stay flat and then go up, right? And so again, you can look at area and stuff to compute how good this is. So apart from just on instances and features, people have also used to evaluate sort of the prototype explanation methods, right? So the idea is you can do the same thing on the training data. You can add or remove the most influential points according to your explanation and see what happens to the model, right? And so here's an example evaluation from a paper in 2019 that was doing exactly the same. You're removing data on the left image and you're adding training data on the right image, and you're seeing how fast your curve is falling or the curve is rising, and the blue is better than the others in this case. Okay, so that was the first way of understanding behavior. Another really common way of doing whether somebody understands the behavior or not is to do something called simulation. The idea here is you have some data and your classifier that you're explaining. You get the predictions and explanations on that data, and you show this to the user. And this is called the training phase sometimes, where you show it to the user and essentially get the user to understand what the classifier is doing through predictions and explanations. Then at test time, you give the user some new data that they haven't seen before and ask the user to guess what the classifier would do on this new data. Then later on, you can actually run the classifier on this new data and see what the classifier actually did, compare the accuracy, compare the predictions to see how accurate the user was. And if the user understands the model through the explanations, this would be really high. Otherwise, it'll be pretty low. Lots of people have done this. This is an example UI of what this might look like, where they're trying to see what the model would predict. And there's a user has to select, in regression in this case, a number of what the prediction should be. And they have to express how confident they are in that guess. OK. The second thing explanations are often used for is whether we can find errors in the model and maybe fix them. So that's whether it's useful for debugging or not. I'm going to go through a bunch of different scenarios and how this is applied. The first one is just to detect problems in classifiers, right? So you take a classifier that has some bug in it, you send it to an explainer, get some explanations, show the user the explanations, and essentially ask the user, did they find a bug or not, right? So for example, if we show them this explanation of this wolf and say, I want to predict, the classifier predicts this to be a wolf because of this lime explanation. In this instance, would you trust this model, right? And the user basically should say no. So you just calculate how often they say no, right? That's the evaluation. Like, do the explanations show that there's a problem with this model? You can also somehow go more fine-grained, where you ask them, what is the classifier doing, and get them to answer in some form and see if they actually got it right? So if you know what the bug is, do the users also figure that out based on the explanations? Another way to do debugging is to just compare two classifiers, where this is sort of a proxy for model evaluation. So you take two classifiers, one is good, one is bad. You explain both of them, show the users two explanations, and say, hey, which one do you think is better? Which classifier is better based on these explanations? And essentially see, when you ask that user that question, do they get this right or not, right? And you know which classifier is better or not, maybe based on some held out data. So here's an example. You can look at this wolf case. One classifier is the snow one that looks at the snow. The other one actually looks at the fur to figure out which one is the better classifier. And the user, based on these explanations, should hopefully pick the correct classifier. The third way of doing debugging using explanations is to find errors in the training data. There have been a few work that are doing that as well. And mostly this is specific to prototypical explanations that are actually explaining all the way back to the training data. So the idea is you have some training data that you add some noisy data to, some data that you know is wrong or has some bug in it. You train a classifier which will be buggy because it's trained on buggy training data. And you explain the output of that classifier to the user. And essentially, you ask the user to sort of look at the highest, training instances that are most important, and essentially relabel them yourself, right? So try to get rid of the buggy stuff in it, right? And if the explainer picks the buggy instances very often, then the explainer is good. If by relabeling them, the classifier gets better, then also the explanations are good. So this is another way debugging is used to evaluate explanations. Okay, so those were sort of debugging and understanding the behavior. One of the most practical ways explanations are used is just for users to help make them better decision makers, right? So essentially, you have to think about this as a situation where there is human AI collaboration going on. And you want to know whether explanations can fit into this sort of a paradigm, right? So this is a nice figure from a paper by Lai and Tan, where they show the sort of spectrum of full human agency on one side and full automation on the other, and how explanations can fit in multiple places in everything that's in the middle of these two extremes. And so, yeah, maybe you show them explanations and help them decide, or you show them machines, predictions, and explanations and get them to decide, and so on. Here's a different way of using explanations that's not very common, but I think it's very exciting, which is to do machine teaching, right? So for example, if I give you one example each of these butterflies, Monarch, Viceroy, Queen, and Red Admiral, and ask you to now figure out which butterfly is which in the wild, you may not be very confident because you don't quite know what makes them different from each other, right? Especially Monarch and Viceroy, like what is actually different from each other. What machine teaching does is trains a classifier on the same task with a lot of label data. And then instead of showing users just the predictions or just the labels, you show them the explanations of that classifier that has seen a lot of label data. And if the explanation method is good, it will exactly highlight the parts that the user should be looking at. And so the user can learn how to identify butterflies by using the explanations, whereas otherwise they wouldn't be able to. Yeah, so I would recommend reading that paper if you're interested in these kind of things. Okay. So those were sort of the higher level ideas of how people have tried to evaluate explanations. And there are lots of people, different ways that they've been sort of approaching this. Unfortunately, and I think there is sort of a lot of problems or limitations in the current way of evaluating explanations. The biggest problem is that the setup is often quite easy or simple, right? So in some sense, they're set up for explanation techniques to just work, making them a little bit unrealistic. In real world, the explanation techniques may not be anywhere close to being as efficient as they are in these simple setups. So for example, the bugs that people add are often very obvious, or the classifiers that you're comparing are very different from each other, and explanations can often work in these sort of extreme cases. Sometimes the evaluation can even be flawed, and I'm not going to point to specific papers, but sometimes the idea is that when the users are, when you're showing users explanations and asking them whether you like the explanation or not, that's a more of a human explanation, and that's what you're evaluating. But in many cases, the explanation techniques are to explain the model, not just what the users like. And so it can get a little bit fuzzy as to what is a good evaluation and what is not. Finally, there are a lot of automated metrics for explanations. And of course, when you have automated metrics, you can also try to optimize them and get a better explanation technique that fits those metrics better. And there is some of that also going on. And finally, I think this is one of the problems fundamental to study in interpretability, is that the user studies that we do are often not very consistent. Essentially, the results can be affected by the choice of UI, by the choice of phrasing, visualization, which population you're evaluating on, how you set up the incentive structure, a lot of these things. And it's never clear sort of whether reproducing these results actually would give you the same results or not, right? Essentially, the problem is that machine learning researchers are not trained for this, and we should be listening more to HCI folks to sort of understand how to do user studies better if you want to make big progress in interpretability. And so overall, because of all of these reasons, the conclusions in many of the interpretability papers, explainability papers, are essentially very difficult to generalize. You never know in your specific case whether it would work or not. So that's all I have for evaluation of explanations. I think in the next section, we'll talk a lot more about the limits, and then we'll talk about the future of this work.
So now we'll move to a discussion of the limits of posthoc explainability. So the limitations we'll discuss in this section fall under 4 different categories: faithfulness or fidelity, fragility, stability, and whether explanations are useful in practice. So let's start with faithfulness and fidelity. So let's say we're given a model F theta here. You can think of this as an inception V3 model trained on ImageNet, and it's given a prediction of Junco bird on this particular input. As we discussed before, we can compute a saliency map on this to explain the prediction Junco bird for this particular input. And the question of faithfulness really asks whether the explanation, in this case, the saliency map that we computed, really reflects the underlying associations that the model learns from the data. And more specifically here, the faithfulness question gets at whether the strongly highlighted portions of this saliency map really reflect the parts of this input that the model relies on to make a classification Junco bird. And so more generally, the task of faithfulness of an explanation function really refers to whether the explanation method produces explanations that reflect the underlying behavior of the model that has been explained. And as we'll see shortly, several different explanation methods don't actually reflect the model that they're explaining. So one way to assess the faithfulness of an explanation method is to assess the sensitivity of the explanation function to the model parameters. And in this case, to make it more concrete, let's say we have an inception V3 model trained on ImageNet and as parameters set in 1, and then we have parameters set in 2, where we've reinitialized the weights of the inception V3 model at the top layer. So think of the final layer as being reinitialized in this case. If we then feed this input into these two different models, we expect the prediction from the parameter set in 1, which is normally trained model, to be accurate as expected, and from the parameter set in 2 to be wrong because we've reinitialized the weights at the top layer. Now the sanity check here is that we expect the posthoc explanation of this model for parameter set in 1 to be different than parameter set in 2. And so if an explanation method really is sensitive to the model parameters. So let's look at an example. We'll consider a guided backprop saliency map for an inception V3 model that was trained on ImageNet. So if we compute a guided backprop saliency map for the Junco bird input as shown here, we obtain the saliency map as shown, and then we can reinitialize the top layer weights and then visualize the saliency map for the input again, and we obtain an output that looks visually similar to what we saw before. It actually is very difficult to identify differences between these two saliency maps. And we can continue this reinitialization by reinitializing the weights of the model from the top layer all the way to the input. And what we'll observe is that guided backprop is invariant to the higher level weights. So this behavior that we just saw for guided backprop is actually sort of general for a class of methods that have been referred to in the literature as modified backprop approaches. These are saliency methods that compute feature relevance by modifying the backpropagation process, usually by positive aggregation along the way while computing feature relevance. And some of these methods have been shown here, like red grad, deep tailor decomposition, variance of the layer relevance propagation. And the finding here that was recently produced by Singh et al. In an ICML paper earlier this year was that the behavior of this class of models is actually similar to that of guided backprop in the sense that they are invariant to higher level weights of a model. So the source of this invariance has also been studied. Initially, Neer et al. In an ICML paper in 2018 showed that guided backprop and DecomNet essentially partially approximate the input. And for the recent work of Singh et al., they showed that this modified backpropagation methods essentially produce outputs that typically would have converted to a RAC1 matrix, which sort of explains the invariance that we observe to the higher level weights. And so the methods that fall under this category are shown here. There are several more, but we're sort of highlighted a few of the ones that are popular in the literature. So not all methods are invariant to the higher level weights. We're showing a few here: gradient, smooth grad, integrated gradients, gradcam, which undergo the sort of differences and changes when the weights of the model is reinitialized. So that ends the discussion on faithfulness, and we'll move to a discussion on fragility now. So the high-level takeaway from here is that post-hoc explanations are fragile and can be easily manipulated. And so to give you an example of that, we'll use a case study from the work of Dombrowski et al. And here, so let's say we're given this image of a dog, and we compute the saliency map for a prediction on this image from, say, a VGG16 model. And we obtain the saliency map as shown. We can adversarially modify the original image. We'll discuss this modification shortly, and then recompute another saliency map, and we obtain an explanation that is completely manipulated. And this is essentially the point in this section, that post-hoc explanations can be easily manipulated. Critically here, these two images actually have the same prediction under the model that is being considered. So in a different case, there are other kinds of attacks that have been proposed in the literature. So Slack and Hilgard in 2020 proposed a scaffolding attack where they were able to hide a classifier's dependence on gender from a LIME and SHAP explanation method. So let's now look at the actual formulation of how to compute some of this adversarial perturbation. The goal usually is formulated as an optimization problem where you want to compute explanations that are maximally different. Here, delta is the adversarial perturbation that you're trying to learn, and then you want delta to be as small as possible because you want to sort of preserve some kind of perceptual quality of the image and keep the differences to be small. And critically, you also want the prediction on the modified image to be identical to the prediction on the original image. And so the formulation here is very similar to the formulation for also producing adversarial examples. And so consequently, you can use variations of projected gradient descent to also compute solutions to this optimization problem. This formulation is due to Gobrani et al. From 2018. So there are several other attacks that have been proposed in the literature, but to sort of remind you of the takeaway from this section is that almost every method that we discussed in this tutorial can be adversarially manipulated. And this speaks to an increasing challenge in this field that needs some more work by the community. So before moving on to other limitations, let's quickly highlight a recent work of Anders et al., who proposed two defenses against explanation manipulation. And these defenses, the hyperplane method and the autoencoder method, rely on the low manifold assumption. So the assumption is that the data lies on a low manifold. And here, the example we're showing is a case where a classifier sort of almost exclusively relies on gender. You can manipulate the explanations of that classifier to shift the dependence to income and taxes. And then if you apply sort of the defense as proposed by Anders et al., you can recover the original explanation as one would expect. More work still needs to be done to extend this line of work to higher dimensions and different data modalities like text and other cases. So now we'll move to a discussion on stability. So the limitation of stability really gets at the fact that some simple non-adversarial changes to the input can lead to drastic changes in the explanations produced, indicating that some of these explanation functions or explanation methods are unstable. And so in a recent work by Alvarez et al., they proposed a notion of stability called the local Lipschitz constant. You can think of this as a measure of how much the output of an explanation function changes due to changes in a ball. You can think of it as an epsilon ball around a particular input. And this sort of captures the idea of a local Lipschitz constant of an explanation function. And so you can empirically assess the local Lipschitz constant of a variety of different explanation methods, as shown here: saliency, gradient times input, LIME. And Alvarez et al. Found that the LIME explanation method was actually had a higher local Lipschitz constant compared to several of the other methods that were empirically assessed. More recently as well, Ye et al. Analytically actually derived bounds on the sensitivity and the fidelity of a variety of different explanation methods. And so another issue that has been raised recently from the work of Bansor, Agarwal, and Nguyen et al. From 2020 is that several different explanation functions are sensitive to parameters like the random seed, the number of perturbations, the patch size, things that don't have no material effects on the function that you're trying to explain. So the model doesn't depend on the random seed. It doesn't depend on the number of perturbations in the explanation function. Yet, changes in these different parameters affect the explanation output, which is not a desirable property. And so more work needs to be done to be able to allow the explanation methods to not be sensitive in this matter. So we'll now move to the last limitation around whether explanations are useful in practice. So explanations have been shown to be able to help identify Sparse signal in the training set. So we looked at an example earlier in the tutorial of a lime explanation revealing a Sparse signal of a snow. More recently, a variant of the LRP explanation method was used to identify the reliance of a model on captions in an image in order to identify the horse class for a Pascal VOC dataset. More generally, explanations have been shown to be helpful for sort of reducing reliance on Sparse training signals. If you train while penalizing explanations, the model also can be more robust to adversarial examples. Explanations has also been shown to be helpful for end users to better simulate the output of a model. And so these are all desirable properties of explanations that have been demonstrated in the literature. However, now we'll discuss some downsides that have also been shown in the literature. In a recent work by Lakkaraju and Bastani from 2019, they showed that it's possible to generate high fidelity explanations or highly faithful explanations that also mislead end users in making the wrong decision. And so in this case, they tested these explanations with domain experts and found that the domain experts had a higher level of trust in the misleading but high fidelity explanation. In a particularly devastating example, a recent work from Potzavi Zangde from 2019 showed that Amazon Mechanical Turk users were unable to use the coefficients of a linear model to better debug model mistakes in the housing prediction task. And this is a particularly challenging setting because a linear model, as machine learning researchers, we think of a linear model as more interpretable, easy to understand and work with. Yet in this case, we have a linear model with a small number of coefficients, but end users have a difficult time interpreting the coefficients of a linear model, indicating that more work needs to be done to better communicate model behavior. Along similar lines, recent work was also done to sort of perform a user study where end users were shown saliency maps from different models and asked to use the saliency maps to debug the model. And the takeaway from here is that the end users relied more on the model predictions as a way to audit and debug the model rather than the model explanations or the saliency maps. More recently, in the work of Borowski and Zimmerman, they showed that natural language images were sort of more useful and helpful for end users to be able to identify which image will strongly activate a particular intermediate neuron in a deep network, as opposed to outputs of feature visualizations, which is somewhat unexpected. So let's recap what we've learned so far. We saw evidence that explanations have been useful for sort of reducing reliance on spurious signal and producing models that could potentially be more robust to adversarial examples. Yet we've also seen a series of studies that have shown that explanations are not as helpful in practice with end users. So what this calls for is more rigorous studies that are clearly defined, that test methods under well-specified settings for well-specified users and well-specified tasks to be able to identify when a method is useful and for what purpose it is useful for. And so there's some emerging work that we highlighted in here, and there'll be more discussion on this issue later in the future section. So now to conclude, we've discussed faithfulness, fragility, stability, and whether explanations are useful in practice. Now this brings us to the conclusion of the limits of post-hoc explainability. We'll now move to this next section. Thank you.
Now let's discuss about the future of post-hoc explainability. In this section, we are going to touch upon a number of potential future directions. To make this discussion easier, we are going to divide or categorize this discussion into two high-level umbrellas. The first one being towards better post-hoc explanations, and the second one being other emerging directions. Let's begin by discussing how can we develop more reliable post-hoc explanations. We have just studied in the previous section that post-hoc explanations have several limitations, like not being faithful to the underlying model, being unstable and fragile. In order to fix some of these issues, recent literature has proposed some interesting solutions. The first one being modeling uncertainty in post hoc explanations. For example, there has been some recent research which proposed Bayesian versions of LIME and SHAP with closed form solutions, and these approaches can be used to generate explanations with confidence intervals. Right? So that can be very useful because this will help us understand the goodness of the explanation that we are getting. The second approach that is being taken is to generate post hoc explanations that are stable as well as robust to distribution shifts. And in order to achieve this, adversarial training is being used in some recent work. The idea here is to basically generate perturbations of data points and then minimize the worst case mismatch between explanation and black box model predictions. Another solution proposed to make post hoc explanations more reliable is to generate causal explanations that are faithful to the underlying model. The idea here, or one of the key ideas that was proposed here, is the causal concept effect, where the idea or the intuition is to estimate the causal effect of a human interpretable concept on a deep neural net's prediction. Okay. All right. So, identifying the vulnerabilities in existing post hoc explanation methods and proposing approaches to address these vulnerabilities is going to be a very important research direction going forward for the success of post hoc explainability. Now, let's talk a little bit about the theoretical analysis of post hoc explanation methods. There has been some recent work which carried out a theoretical analysis of LIME under the conditions that the underlying black box is a linear model and data is tabular and discretized. What this work does is to obtain closed form solutions of the average coefficients of the explanation output by LIME. And this work also showed that the coefficients obtained are proportional to the gradient of the function to be explained. And another important finding of this work is to demonstrate that the local error of the explanation is often bounded away from zero with a very high probability. Okay, so such theoretical analysis and maybe even deeper theoretical analysis which shed light on the fidelity, stability, and the fragility of post hoc explanation methods are extremely valuable for the progress of this field. Now, let's come to the third piece under our first umbrella, which is rigorous evaluation of the post hoc explanations. Now, there has again been recent research which basically demonstrates some very alarming pieces here. The main insight being that domain experts and end users seem to be over trusting explanations and the underlying models based on explanations. For example, one of the recent works showed that law school students were trusting underlying models about 10 times more when they are shown a misleading explanation which whitewashes the model. Similarly, there has been other work which shows that data scientists over-trusted explanations without even understanding what the explanations are. And this work also points out that it almost seems like participants trusted these tools, not because they really understand them, but because of the visualizations and their public availability. And here are some snippets of the responses from the data scientists from the study. And what you can clearly see is one of the users mentioning that they don't fully understand what the method is doing, but since it is pretty popular, they're okay going along with it. Now, Another piece that is an interesting evaluation is to basically understand the effect of explanations on human AI collaborations. Again, there has been some recent work which does this with respect to sentiment analysis and question answering tasks, and the insights obtained from this work is that the state of the art explanations, for example those obtained using Lime, made little to no difference to the human AI collaboration performance, and in fact showing the explanation sometimes actually hurt. So, given that we have all these interesting and sometimes alarming insights, it is important to continue doing more rigorous user studies and evaluation to really understand how useful are post hoc explanation methods in different contexts, under different settings. And this understanding is going to be extremely critical for the progress of the field. Now let's talk about some other emerging directions. A lot of this talk has been about post-hoc explainability in the context of classification, but there has been some interesting work happening on post-hoc explainability even beyond classification. For example, in the context of RL. There has been some work that basically uses the model distillation techniques, for example, using soft decision trees to understand RL policies. Okay, the idea here is to basically map states to actions using decision trees. There has also been some work which summarizes agent behavior by identifying some of the important states in a policy. And a state is considered to be important if different actions lead to substantially different outcomes from that state. Similarly, there has also been some work on producing causal explanations which can capture the behavior of RL agents. The idea here is to generate these explanations based on the counterfactual analysis of the causal model. For example, what you see here is the case of explaining the actions of a StarCraft agent, and an end user can ask a question like, why not take this action of building barracks? And you will see the explanation that it is more desirable to take another action of building supply depot than building barracks, because to have more supply depots is basically the end goal, right? So that will help us have more destroyed units and more destroyed buildings. Okay, and beyond RL, there has also been a lot of discussion or recent research on explainability in the context of other approaches or models like graph neural networks. For example, GNN Explainer is a recent approach that takes a trained graph neural network and its predictions, and it returns explanation in the form of a small subgraph and a small subset of node features that have played a key role in that particular prediction. So lots of real world applications call for models and algorithms that go beyond classification, and there are lots of exciting opportunities to explore explainability in these kinds of settings as well. All right, now there are also other emerging directions which basically involve thinking about intersection of explainability with other areas under the umbrella of trustworthy ML. The first one that we would like to touch upon here is intersections with differential privacy. There is a real risk that explanations could potentially expose sensitive information from the data sets. For example, explanations of complex black box models, can actually tell us a lot about what kind of data is there underneath and so on. So we want to build explanations which are not only interpretable but also differentially private, and that is exactly what some of the recent works have been doing. For example, one of the works basically tries to achieve this goal by using locally linear models and then perturbing the gradients when learning these models. Of course, there's a clear need for more theoretical, methodological, and empirical research exploring this intersection. There are also some interesting works at the intersection of explainability and fairness. For example, there have been some recent approaches which try to basically understand if a model is biased by doing this approach of, or this intuitive idea of distill and compare. That is, let's say we have a black box model. We first carry out model distillation like we studied earlier and approximate this black box model using a simpler interpretable model. Okay, and then you basically take the true outcome or the data and then fit the same class of simple interpretable model. Now you compare these two models to basically detect biases in the black box model. Okay, that's a technique that has been proposed by Tan et al. In recent work. Now, there are also other works that touch upon this intersection. First of all, normally I'm pretty sure several of you have seen that it is a common hypothesis that post-hoc explanations can help with detecting model biases. Of course, there needs to be a lot more rigorous theoretical and empirical analysis to evaluate this hypothesis to prove it wrong or right. Can post hoc explanations help detect unfairness is, of course, a valid question to ask, and that some of the works also explore. In addition, we also need to think about what notions of unfairness do these biases exposed by post hoc explanations help us identify. So, that is another critical question to answer. Now, there has been also some very recent work by Begley et al., where the idea is to basically come up with these fairness Shapley values, where we attribute unfairness in model predictions to individual features which are using the, which can be done by using the Shapley values framework. And for different definitions of fairness, it is possible to choose Shapley functions which explain the unfairness. This is another interesting piece of work that we would encourage all of you to look at. So, the connections between explainability and fairness need to be explored more thoroughly, both through rigorous theoretical analysis as well as user studies. With that, we have come to the end of this discussion on the future of post hoc explainability. Today, we have covered a lot of ground. We discussed various approaches for post hoc explainability. We touched upon evaluation of post hoc explanations, shed some light on the limits of post hoc explanations, and also discussed the exciting future ahead. We would like to leave you with some parting thoughts. When proposing a new explanation method, please think about who the target end users are that the method will help. It is important to include in your research and write ups a clear statement about what capability or insight the method that you are proposing aims to provide to its end users. It's also important to include a careful analysis and exposition of the weaknesses and vulnerabilities of the proposed method. It is also important to carry out rigorous user studies, preferably with actual end users, to really evaluate if your method is achieving the desired effect. Lastly, please use quantitative metrics to make claims about explainability and not just anecdotal evidence. Thank you.
Thank you very much for your time and attention. We hope you found the tutorial helpful and insightful.
We would like to explicitly acknowledge that explainability is a burgeoning field and there is a lot of interesting work coming up. However, due to time constraints, we were unfortunately unable to exhaustively cover all the amazing work out there.
We do have a companion webpage with a more detailed list of references, along with links to the slides and video of this tutorial. We have also linked another tutorial that's a little bit more detailed in case you're interested. So please just check those out. Thank you for attending this tutorial.